Okay, so let's go ahead and finish that second page. Kind of feel like I almost wish the review was a little longer. It's pretty brief overview of what we're doing, but sometimes it's nice to be short and sweet. Hopefully, practice those skills in other places and don't think this is sufficient to be fully prepared. It's just more of like a friendly reminder. But anyway, let's see what we got here. So first thing it says, let's find the area under the graph, which we of course know has to do with this idea of finding an integral. So we're going to start by finding the integral of g of x, which is x to the negative 3/4 plus 3x to the 5/3. Don't forget the dx. Now it says express it as an integral, and of course that's just being able to set up that finding that area is represented by this. So again, this is a very introductory test. So, being able to know how to translate this story into this symbolism is fairly simple, but we need to make sure we know that. Now, of course, this is playing our power rule game. So the ultimate goal when we have the ability to take an actual integral is what we call a definite integral, because it is defined on this interval, is to increase the exponent by 1 and then divide by that new exponent. But dividing by 1/4 is the same as multiplying by 4. Moving over here, that's going to be x to the 8/3. If you take 5/3 and go up by 1. Now I need to divide by 8/3, which is really multiplying by 3/8. So I have my 3 right here, but I'm going to multiply that by 3/8 because of the antiderivative story from 1 to 3. Now, you might think, oh, that's going to be pretty nice. 4/4 roots of x plus 9/8 x to the 8/3. Evaluate it from 1 to 3. Although, let's say, you might get away with something nice in this position right here. We're plugging in a 1, but plugging in a 3, it is not going to be very pretty. So I did that separately off screen, and I've got 5.264 plus 21.061 coming off of the first part. That's plugging in the 3 into both of these. Then we're taking away the result of plugging in the number 1, which of course, plugging in 1 here is going to get 4. Plugging in 1 right here is going to get 9/8. And all of that combined together, if we were going to make that into a nice little decimal, is 21.200. Okay. Again, this is one of those things where if we're going to leave it in exact form, I literally have to leave it as the 4th root of 3. And, I don't know, 3 to the 8/3 is not going to be nice. It's the cube root of whatever 3 to the 8th is, which is a rather large number. But, okay, so this is the ones that I wanted to get to. So these two right here, and I think I want to start with number 10 because it's actually the easier, the more direct of the two problems. So an antiderivative here would be pretty simple, 3/2 x squared minus 2e to the x, because the derivative of e to the x is e to the x. So the antiderivative is the same. And again, evaluating it from -2 to 0. Sometimes, we use a calculator, sometimes we don't. And I just wanted to model this time. I'm going to go ahead and avoid using the calculator because if I plug in 0, I do in fact get 0. And minus 2e to the 0 is anything to the 0 power we know to be 1. So that looked like it might be difficult, but it turns out plugging in 0 makes it simple. Now, if I plug in -2, -2 squared is 4. 4 times 3 is 12, over 2 is 6. And then, of course, if we plug in the -2 here, that would be minus 2e to the -2. So grand total together, I have a -2 here and a -6 here, making a total of -8. And there's a double negative, so I'm getting a +2 over e squared. And that would be a precise answer. Now, as far as checking it with a program, we could actually go through the thing and do F and I and T. Now, again, this is not calculator notation. This isn't like math notation. This is more calculator stuff to see if, in fact, we did that math correctly. So probably worth doing real quick. Even on an easy problem, it's not a bad way to go. I'm going to go ahead and do this problem in a very specified way that I actually just recently learned how to do. So here we have my problem, and I'm going to go to math 9. That's my numerical integrand. I want to go from -2 to 0. And this is the place that I thought was really interesting, is I didn't really know it, but if you hit alpha, the green button alpha down here, alpha trace, it brings up this special little menu, and then my Y1 is sitting right there. Now we could do the vars, Y vars thing, but alpha trace is pretty efficient as well. So this is what I got. And of course, my actual answer that I decided to try was this one. And it looks like we did perfectly. So I'm very, very confident in that answer and can move on. Now, number 9 is actually not a difficult question at all, but it's one that sometimes people just like get into the weeds on, because what they don't think of is that sometimes your best bet is just to do some simple algebra first. So the first thing I'm going to do is rewrite this problem as x squared plus 8x plus 16. Because we know that you can multiply those things out. And to me, the big key is this idea: if you ever have a monomial, meaning a single item denominator, when you add fractions back and forth, remember, when you add fractions, you get that common denominator, you put the numerators together, but that means you can actually reverse that project. And therefore, that would mean x squared over x is x, 8x over x is 8, and 16 over x is what we would have left, being evaluated from 1 to 3. Well, that took it from a very difficult problem into a phenomenally simple one. And so our antiderivative is half x squared. I got 8x, and this is the one that people have trouble with. Remember that the integral of 1 over x is a natural log. And that's going to be evaluated then from 1 to 3. And of course, we just need to plug that in. When I did, I ended up with, just not wanting to make this video particularly long, go through the math. I got 20 plus 16 natural logs of 3. Keep in mind that the natural log of 1 is 0. So, a lot of the stuff cancels out pretty nicely, and we can check it. Now, I did want to mention something that kind of came from the earlier video. When you divide by x, that does create a problem, but keep in mind that problem would happen at 0, and we're only interested in the region from 1 to 3. So the discontinuity that was affected by that domain error is actually not part of my story. Okay, so moving on to number 11, we're given an acceleration of this object, and we want to find the change in velocity from that time. So you want to keep in mind, if we're going to find the change in velocity, we want to know the integral, because again, the antiderivative of acceleration would be velocity. And we're specifically asking what happened over the span of from 0 to 5. So we've got 2 plus 5t to the 1/2 dt. Again, embracing power rule is always a smart thing to do. So I'm going to have t to the 3/2. Now, when I divide by 3/2, that's multiplying by 2/3, evaluated from 0 to 5. Of course, evaluating that at 0 is a trivial answer. So I'm just going to go ahead and write it this. I could say 10 plus 10/3 square root of 125, but 0.268 would be fine, and it might be something like say meters per second, and that's what is changed in the velocity as it accelerates. Now, when you ask how far it traveled, that's going a little bit further, because the antiderivative of acceleration would be velocity, and the antiderivative of velocity would be position. And so we're looking at 0 to 3, 2t plus 10 over 3, 3/2 dt. We're taking another antiderivative. And so we go through that, we're going to get t to the 5/2. So I'm going to multiply by 2/5, which gives me 4/3, evaluated from 0 to 3. Now, as it turns out, this answer is 9 plus 12 roots of 3, because it actually comes out fairly nice. I will say there is a little bit of a fallacy to this problem. There's something a little bit wrong that we talked about, because this would be true if we knew the velocity at time zero was zero. And this was never stated in this problem. So, we've talked about the fact that there can be a constant that disappears. See, if I took the derivative of this position function, there would be some kind of a constant sitting inside this velocity, but then the antiderivative, that constant, would actually reappear over here, and it's not to be had. So I would say there's a little bit of a flaw in this question, but the principle behind the idea of finding velocity off of acceleration is actually fairly accurate. But small mistake in there in terms of the setup, because we haven't really started trying to push the initial condition problems. Now again, this one I am a little bit cautious about, because spacing isn't always constant, but in this particular case, it does say the horizontal spacing is 3 feet. So remember, our trick for trapezoid rule was cutting the first in half, leaving everybody else constant until you get to the first and the last, and cutting them in half to get that spacing. Fairly simple operation, just pressing a lot of buttons. And I would probably recommend doing that a couple of times and really meticulously watching, because if we hit a mistake on our buttons on our calculator, there's no way to know that you did that, if you're not careful. And I've done that many times where I get the wrong answer, and it's just because I just missed one of the decimals just right. Okay, I will see you back in class. Hopefully that helped. Right.